Good morning. So good morning. So before starting with the class, once again I will explain whatever we have discussed in the last class, right? So what and all we have discussed? We have discussed about anionic detergent, then cationic detergent, then non-ionic detergent. That's where we have the different types of detergents: anionic, cationic and non-ionic, right? So good morning to everyone. Fine. So in that case, when I am talking about anionic detergents, I have given the example of SDS, that is nothing but sodium dodecyl sulfate, so which can also be called as sodium lauryl sulfate, right? So that's where we have the anionic detergent. When it comes to cationic detergent, it is CTAB, that means cetyl trimethyl ammonium bromide, that is CTAB, cetyl trimethyl ammonium bromide, SDS CTAB. So don't write short form in the exam. If they ask example for anionic detergent, don't write simply as SDS. Sometimes you may get the marks, but still you should write what is actually the name of the molecule. Fine. So that's where we have anionic detergent, cationic detergents. And when it comes to non-ionic detergents, we have discussed about stearoyl polyethylene glycol, right? So we have discussed about stearoyl polyethylene glycol, where stearic acid was made to react with polyethylene glycol, right? So that's what we have discussed with respect to chemistry in everyday life. Okay. Now when I am talking about next chapter, that means polymers. We started with the polymers, right? So we were discussing about classification. We were talking about classification of polymers. So that's where we have natural polymer, then we have semi-synthetic polymer, then we have synthetic polymers, right? As the name itself indicates, natural means which occurs natural in the environment, not man-made. So that's where we have natural polymer. Semi-synthetic means whatever natural one is there, we will slightly modify that one. But synthetic means which is not at all present in the nature. It is completely human made, right? So that's where we have the natural, semi-synthetic and synthetic polymers. Then what else we have discussed? We have discussed based on the shape, right? So that's where with respect to shape or structure, that's where we have discussed about linear, branch and cross-linked polymers. And when it comes to linear, cellulose, natural polymer, cellulose can be example, PVC can be example, Teflon can be the example. So all of them, they are example for linear polymers. So when it comes to branched, I have discussed about low density polythene, which can be one of the example for the branched polymer. Cross-linked polymer, bakelite can be the best example. Even one of you only had told melamine, which is absolutely right. So even melamine can be the example for cross-linked polymers. Okay, another important point. Yesterday someone had asked about BHT and another one is BHA, polyhydroxyanisole and polyhydroxytoluene, right? So as I have told, these chemicals will act as an antioxidant by donating the hydrogen atom. Fine. So whatever OH group is there in their structure, they will donate that one and they will donate hydrogen atom to the radical. Whatever radical is there, it will donate, because radicals are those species which are having lone electron. So hydrogen is also having one electron, so they will make the bonding. So that's how BHA or BHT will act as a antioxidant. That's what I was telling in yesterday's class. An antioxidant can act as by donating the electron, or by taking the electron, or by donating the hydrogen. So we have different mechanism, but BHT and BHA both will act in the similar pattern, that is by donating the hydrogen atom. But anyway, they used to use it for as a food preservative earlier. Now they have decreased because some of the research tells that they have the cancer causing agent. They are acting like a carcinogen. Some of the experiment on the animals, whatever they have performed, based on that they are finding that they are having carcinogenic property. Okay? Okay, fine. I will come back to the topic. So that is related to, okay, Sanjana. Okay, fine. So we will come back to the topic, that is classification. That's what we have discussed in the previous class, right? So that is based on the source and based on the structure. Now we are going to discuss about classification based on, here classification is based on intermolecular force. Classification can be based on intermolecular force, right? So in that, first one is elastomers. First one is elastomers. Once they had asked about elastomers, right? So elastomers are those polymers which are having least intermolecular force. They are having least intermolecular force. Between the monomers it will be there, but between among the monomers I am talking about. Means monomer chain will be there, right? Polymers. So among these polymers I am talking about the interaction. Fine. So elastomers will have the least interaction among the polymer subunits. Fine. So due to the least interaction, they can be expandable or they can be contractable, because due to the less amount of force involved. So that's what we will tell, elasticity, right? So that is same logic. That's why they are called as elastomers. Now naturally all of us we know our rubber, whatever eraser we are using, natural rubber, even natural rubber can be the example for elastomers. Even Buna, they can be the example for elastomers. So what are elastomers? These are the polymers having least interaction, right? And due to the low amount of interaction, they can be expandable and they will come back to its original position. That's why, or shape. That's why it is called as elasticity. Fine. So that's where we have the elastomers. So these are the some of the examples. Now, next one is fibers. Next one is fibers. Now, in the name itself it is there. Fibers, whatever cables and all we are using, they will act as a fibers, and all of us will know they should be very strong. They should be very strong. So naturally, Ravikant, I think here there is no problem with network, because I can see video is continuing. Okay, no clarity. So not clear. Oh, many students they are telling. But I think here it is clear, Appa. Oh, board is not clear. Fine. Whether now all of you can see? Okay, now it's fine. Okay, in that case I will start with the class. Now whether you can see whatever I have written on the board? Okay. Okay, fine. Thank you. So that's where we have the elastomers with least interaction. These are the example. Natural rubber and Buna can be the example. Now when it comes to fibers, right? So they will be having strong force. They will be having strong force which will be holding them, which will be holding more polymer units. They will be holding. So that's where fibers are having strong force. Especially they will be having many number of hydrogen bond. They will be having many number of hydrogen bond. Fine. Single hydrogen bond is weak. But when you have more than multiple hydrogen bond, now it will be a strong. Just like DNA, biology students, right? So multiple hydrogen bond will make DNA stable. Same logic is applicable here. So now they will be having strong force. So one of the example for that force can be hydrogen bond, right? So naturally in this category we can have nylon 6,6 which has the group which can involve in the hydrogen bond formation. It can be nylon 6,6 or it can be many other examples where we can have the functional group which can donate the hydrogen atom or hydrogen bond which can be involved in the hydrogen bond formation. That's where we have the nylon 6,6. Okay, so that's where polyamides. Instead of nylon 6,6 you can give it as polyamides. So that's where we have the fibers. Next one is under same area only. Next one is with related to thermoplastic. Next one is related to thermoplastic. Okay, I will mention this one as important. So I will mention this one as important. Thermoplastic polymers. Same category. Based on the force only, we have discussed about elastomers. Then we have discussed about fibers. Now another one is thermoplastic. Now the speciality of this thermoplastic polymer is this polymer on heating it will become softer. On heating it will become softer. And on cooling once again it will become hard. Once again it will become hard. But very important point here is unlike whatever plastic material we will be using. For example, if you go with bucket, while taking bath and all we are using bucket, right? So if you heat that bucket, it will become soft. And when it will become cool down, it will become hard also. But problem here is, whichever shape it is there, in that form only it will become hard. That's the problem with that type of material, right? They are not reusable. Bucket, if you completely melt it, then it's gone. It's not reusable, right? So they are not belongs to thermoplastic polymers. So thermoplastic polymers are those which on heating it will become softened and which on cooling it will become hard. Like polystyrene can be one of the anyway. All these examples I am going to discuss in detail. Polystyrene or PVC, all of them they can be the examples for thermoplastic polymers, right? So for example, if I take PVC pipe and all which will be used for our electricity supply or water supply, and all of us it will be exposed to environment. Many years together it will be exposed, but still nothing will happen to that particular material because it is thermoplastic. So that slightly it will become expand and once again it will be there only. So major reason for this one is thermoplastic polymers they have intermediate force. They are having intermediate force between elastomers and fibers. They are not having low force as of elastomers, but they are not having many force as that of fibers. So they are intermediate. Which one? Thermoplastic polymers. So therefore, heating they will become softer, but on cooling once again they will become hard to original form. that is to the original form. That is the speciality of the thermoplastic polymers. All of you have understood? So now, some of the polymers will have low branches. They will be having low branches. Some of the polymers, they will be having low branches. Fine? So that's where we have the thermoplastic polymer. So whatever next one I will be telling, I will consider that one also important. That is thermosetting. Thermosetting polymer. Thermoplastic polymer and thermosetting polymer. Fine? Now, when it comes to thermosetting polymer, as I was telling with respect to buckets and all, I was talking about buckets and all now. So that's where thermosetting polymers, what I mean to tell here is, on heating, no doubt it will become softened or it will be melted. But when it will become cool, so it will become fused. It will become fused, infusible. It is called as fused. That means becoming hard is different, becoming fused is different. Fused in the sense which will not have its original shape. So that's where we have the thermosetting polymers. Naturally, cross-linked polymers comes under this category. When it comes to thermosetting polymers, it will be cross-linked polymers which comes under this category. So naturally, example can be anyone cross-linked. Example can be bakelite. One of the best examples can be bakelite. So that's where we have the thermoplastic polymers and thermosetting polymers. Fine? So bakelite, yes Ravikant, very good. So that's where. Now when it comes to thermosetting, it cannot be reusable. It cannot be reusable. This can be reusable. Someone had written, I don't have large board, I have to come nearby. Ravikant, okay, reused. That means this can be reusable, not this one. It will become fused. It's lost. Once it is melted, it will not come back to original form. So that is drawback of this one, but it will be very strong due to the cross linkage which is present between the polymers. Fine? So that's where we have the thermosetting and thermoplastic polymers. Remember this. These two are important. These two are important with respect to your exam point of view. Yes, Ravikant. Urea, formaldehyde, yes, resins, even they can come under this category, no doubt. Fine? So that's where we have the thermoplastic polymers. Fine? So this is where we have discussed about the classification. Now another way of classification is how this polymer has been produced or synthesized. Fine? So another way of classification is, anyway in detail I am not going to discuss this one here. Individually when I will be talking about mechanism of synthesis, that time I will explain in detail. So based on the synthesis, polymers can be classified as chain growth polymers or step growth polymers. That means one is based on the addition reaction. That is addition polymerization. That is addition polymerization. And another one is condensation polymerization. Condensation polymerization. Anything, condensation and addition. So it is purely based on how that polymer has been produced. It can be produced due to addition reaction or it can be produced due to condensation reaction. So normally addition polymerization or addition reaction, all of us will know it will happen when we have unsaturated molecules. When we have unsaturated monomers, here with regard to monomers. For example, PVC, polyvinyl chloride, where vinyl stands for ethene group, right? Vinyl stands for ethene group, polyvinyl chloride, PVC. So that can be due to addition polymerization. Polythene, ethene is there. So that can be the example. So what I mean to tell here is, if you want to give the example, these are some of the example which are resulted due to addition polymerization. These are some of the example of polymers which has been produced due to addition polymerization. If you observe PVC, where vinyl chloride is the monomeric unit. Vinyl chloride means CH2 double bond CHCl. So that's where we have the vinyl chloride, right? So if you observe it carefully, that's where I have the unsaturation, monomeric unit. So if I take Teflon, Teflon is also nothing but tetrafluoroethane, monomeric unit in Teflon. So Teflon is polytetrafluoroethane. Fine. So the same way, polythene, don't worry, these things we are going to discuss. Polythene, once again, ethene, CH2 double bond CH2. So why I am writing this one? Because to make you understand that addition polymerization can happen whenever we have the unsaturated monomers. Clear? All of you have understood? So that is one type of polymer, addition polymers. Okay? So which is also called as chain growth polymerization. Next one is condensation polymerization. Naturally, it can happen when monomers are having bifunctional groups, or monomers are bifunctional group containing monomers. What do you mean by bifunctional group? Two functional groups should be there. It can be same type functional group or it can be different types. Anything is fine. So that's where it demands the presence of functional group in the monomers. So in that case, we have plenty of example. Bakelite, this can be the example. Then we have the nylon 66. That can be the example, right? So melamine, that can be the example. All of them, they are due to condensation reaction. So what is condensation reaction? Simple example is, I have OH group and I have COOH group in a monomer. We'll imagine. Now there will be liberation of water and then there will be formation of ester linkage. There will be formation of ester linkage. This is the basic with respect to polyesters. Terylene. This is the basic reaction with respect to terylene, polyester. In the name itself it is that, polyester. That means multiple ester linkage. So during the formation of this linkage, what is happening? There is a liberation of water. Right? So same way, nylon 66 if you take. That's where I have NH2 and that's where I have COH. Same logic. Here also there will be liberation of water. Right? Now what will happen? There will be formation of amide. It's not peptide bond. NHCO, here in this case I will call it as an amide. So amide bond can be called as a peptide bond when they are present between the amino acid. But here we are not dealing with the amino acid. So therefore polyamide. Polyamides are those which are having multiple amide linkage. Example is nylon 66. Polyesters are those which are having multiple ester linkage. Terylene can be the example. Even that one you can include in the condensation polymerization. So what I mean to tell here is, polymers, when it comes to addition polymerization, no liberation of any side product. But when it comes to condensation polymerization, yes, there is a liberation of small molecules like water, or it can be any other molecule depending on the functional. Fine? So that's where we have the two categories. That's where we have the two categories of polymers based on which polymerization process they are resulted due, or they are resulted due to which type of polymerization process. Whether it is due to addition polymerization or whether it is due to condensation polymerization. That is related to organic chemistry, reaction, right? Addition reaction, condensation reaction. So all of you have understood? So in case of the addition polymerization, which type of monomer should be there? Unsaturated monomers. In case of the condensation polymerization, which type of monomer should be there? It should be monomers containing functional. Fine. So that's what we have discussed. So nylon 66 is formed by the condensation. Okay, that one we are going to discuss, Ravikant. In detail, we have to discuss that one. We will not focus on that one now. We are going to discuss all those things in detail. Fine. So now we will come to addition polymerization. Now we will come to addition polymerization. Okay. Already I have given the view of addition polymerization. How exactly it will be done. But very important point which I have not mentioned there is it demands activation. There should be something which will be involved in the activation of the process. So that's where we will be using peroxides. So addition polymerization depends on the peroxide. Most of the addition polymers, they have been produced due to the or by utilization of the peroxide. Fine. So when I am talking about peroxide, it can be benzyl peroxide, it can be benzyl peroxide, or it can be acetyl peroxide, etc. So before that, what do you mean by peroxide? Or what are peroxides? Any idea? What are peroxide? If you understand this one, then you can understand the whole story. Fine. So what are peroxides? Any idea? So fine. Very simple example is hydrogen peroxide, H2O. Water is H2O, but I am talking about hydrogen peroxide. So now when it comes to water, it is O linked with the 2 hydrogen, right? But when it comes to hydrogen peroxide, so that's where in first year people have studied, that's where we have the hydrogen peroxide. 2 oxygen linked to each other by the single bond. 2 oxygen linked to each other by the single bond. That's where we have the peroxide. Now, speciality of this peroxide here is, since both the oxygen are equipotent, they are same. So they will go for homolytic cleavage. So due to that, there will be formation of radical. Hydroxy radical it is. Not OH minus. It is OH dot. Because they have got 1 electron, 1 electron. So therefore, hydroxy radical. Fine. Same logic is applicable for benzyl peroxide also, where we have the C6H5O, CO, which are linked by the, like this, there will be presence of O, single bond O. Okay, I have written O type. This is not there. So that's why we have the peroxide. Now there will be homolytic cleavage, right? So there will be homolytic cleavage. So due to that, what will happen? So there will be C6H5O, COO. So same way C6H5O, CO, radical, right? So due to the presence of radical, this bond will be cleaved, okay? And there will be liberation of carbon dioxide, and in turn there will be formation of phenyl radical. This is not called as benzyl. This is phenyl radical. Radical always should be shown by lone electron. 1 dot should be there. So phenyl radical will be formed whenever we are using benzyl peroxide. Same way, acetyl peroxide means where 2 acetyl group linked by the peroxide or 2 oxygen atoms. That means diacetyl peroxide, CH3, COO, CO, CH3. Now what will happen? There will be formation of methyl radical. So here phenyl radical. So don't worry, in board exam they will not ask all these things. It may be helpful for your competitive exam. Fine? So that's where we will go with the benzyl peroxide. Whatever is given in your textbook, that example only I will take. So this is where we have the benzyl peroxide, which is involved in the formation of phenyl radical. So which radical will be produced whenever we are using benzyl peroxide? It should be phenyl radical. Remember this molecule. Right? Now, this particular thing, we'll go with the example of polyethylene formation. We'll go with the example of polyethylene formation. Now, whatever phenyl radical is there, now it's going to react with CH2 double bond CH2. Right? It's going to interact with ethene. It's going to interact with the ethene, which will lead to formation of another radical, CH2 radical. Right? Now the growth will start. This is initiation. Whatever step I have written, it is initiation. That means there will be formation of a radical. Now next comes the polymerization. In polymerization, what will happen? Whatever radical has been produced, it will going to form. It's going to continuously react with other monomers, and there will be formation of the radicals. So that's where C6H5, CH2, whatever radical is there, it's going to interact with another ethene, and there will be elongation of chain. CH2, radical. Right? So like that, it will going to be elongated. Polymerization will happen. So at the end, what if I am going to get at the end of this step? I am going to get CH2 n number of times CH2. Right? That's where it is called as elongation or polymerization. Whatever reaction, whenever there is a presence of a radical or radical mediated reaction, always it will have three stages: initiation, elongation, termination. Initiation, polymerization, termination. Anything is fine. You can call this one as elongation or polymerization, fine. So that's where we have got the initiation, elongation. So in initiation, what is happening? A peroxide radical has been converted into phenyl radical, and phenyl radical is making much more radical. Okay, fine. So board is not clear. Once again, 1 minute. Today. Now whether it's clear? All of you can see the board? Okay, now Sanjana, still it is buffering? Okay, fine. Done. I'll start with the class. Fine. Okay, sorry, due to network this one, in between some disturbance is there. Okay, so fine. So that's where we have the polymerization or elongation. That's where we have the polymerization or elongation. First step, second step. And the last step will be termination. Please remember, a radical when reacts with another radical, that's where it is called as termination. A radical reacts with another radical, that's where it is called as termination. Fine? So that's where we have got the termination step, where these type of radical, whatever has been produced, they will react with each other. For example, C6H5, CH2, n number of times, CH2, whatever radical is there, it will react with another same radical which is produced due to same polymerization process. So they will interact and they will make the bond with each other because of the presence of lone electron, not lone pair, lone electron. So that's where we are going to have C6H5, CH2, 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 N and C6H5. That's where we have the polythene. That's where we have the polythene. So C6H5, CH2, CH2N, CH2, CH2. That's what I have written. So this is from one thing, and another part it is present here. So both together they have formed a huge polymer. Both of them, they together they have formed a huge polymer. Fine. So that's where we have the polythene synthesis. So for polythene, same way, for other addition polymerization also, same mechanism. So don't worry, for your board exam and all, they have never asked about mechanism and all, but better if you understand. Fine. So for all the addition polymerization, same mechanism will be involved. Fine. So even it can be applicable for Teflon, even it can be applicable for PVC, whatever. Whichever addition polymers are there, they will follow the same mechanism. So hagadre, what is basically required to initiate the reaction here in addition polymerization? Which is that basically required? Anyone? Which chemical which we have to add initially? Any one of you? Any one of you can tell me which chemical we should add initially? It is peroxide, or any chemical which is going to initiate the radical formation. But normally they are going to use peroxide. Fine. For addition polymerization, there is a requirement of peroxide, which is not required for the condensation polymerization. All of you have understood this mechanism. So therefore, please remember that addition polymerization will depend on the radical formation, and due to that it will be having three steps. First one is initiation, second one is elongation, and the last one is termination. So benzyl peroxide, yes, I have taken the example of benzyl peroxide. Even acetyl peroxide, that is diacetyl peroxide, can also be used. Anything. In your textbook, since they have taken, I think they have taken, okay fine, they have taken benzyl peroxide. Even I have taken the example of benzyl peroxide. Fine. Any doubts? Okay. So in that case, we will move to the next one. Related to this only, related to polythene only. When it comes to polythene, we have two types. And once again, whatever I am telling, it is important. So that means when I am talking about polythene, we have two types. Polythene can be classified as LDP and high DP. That means, what do you mean by DP? Not WhatsApp DP I am talking about. DP means density. Okay? P stands for polymer, low density polymer and high density polymer. So low density polythene and high density polythene. Okay? This is also important. Now, when I am talking about low density polythene, here naturally radicals should be required, that is peroxides are required, no doubt, for both. But along with that, here reaction conditions are different. So in this case, they are going to be with high pressure. They are going with very high pressure. Okay? So it can go up to 1000 atmospheric pressure. Fine? It can go up to 1000 atmospheric pressure. So 1000 to 2000. Fine? So that's where we have the 1000 to 2000 atmospheric pressure. And temperature, I will write approximately, we can go for around 350 Kelvin. It can go up to 350, 500 Kelvin also they will go. 500 Kelvin. So then they are going to get low density polyethylene. Then they are going to get low density polyethylene. This type of polyethylene will be utilized for the synthesis of squeezing bottles. Squeezing bottles. So whatever we'll be using for drinking water and all, we can squeeze it, right? So squeezing bottles, or it can be utilized for the toys. Utilized for the toys. So that's where we have the low density polymer. Now they are having slightly branched. They are the branched polymers. They are the branched polymers. So this is the reaction condition. Now when it comes to high density polymer, now the condition is different. So the temperature can be around 350 Kelvin and pressure can be around 6 atmospheric pressure. Pressure can be very less compared to this pressure. 6 atmospheric pressure. And very important one is, this will carried out in the presence of the catalyst. That is nothing but Ziegler-Natta catalyst. That is nothing but Ziegler-Natta catalyst. So that's where we have the catalyst. Okay. So when it comes to high density polymers, what is that difference? The difference is, one is temperature, next is pressure, and another one is there will be utilization of Ziegler-Natta catalyst. Okay now? Any doubts? Fine. Now, when it comes to Ziegler-Natta catalyst, that is nothing but triethyl zinc with titanium tetroxide. That is nothing but, when it comes to Ziegler-Natta catalyst, it can be tetraaluminium zinc or tetraethyl zinc. We will go with whatever is given in your textbook. Okay, they have given ethyl only. Okay, in your textbook they have given zinc, tetraethyl aluminium, which is in combination with titanium. Tetrachloride. Okay, so this one they will ask in the exam. This is nothing but Ziegler-Natta catalyst, and this is the one which makes high density polymerization, because they will provide the surface for these monomers to react. So that's why we have zinc tetraethyl aluminium. Once again. Tetraethyl aluminium, then titanium tetrachloride. Okay, titanium tetrachloride. Okay, so that's where we have the Ziegler-Natta catalyst. So where they will be used? With respect to high density polyethylene. Now high density polyethylene is the one which will be used in the buckets and all, whatever we will be using in bathroom and all, to storage of water. So those buckets and all, it will be prepared by the high density polyethylene. So squeezing bottles, toys and all by low density polyethylene, and high density polyethylene will be used for the manufacture of all these buckets and other utensils. Fine. So that's where we have the Ziegler-Natta catalyst, and remember about the chemical name. Fine. Any doubt? If you don't have any doubt, once again we have to discuss about addition polymers only. Another one is Teflon. All of us we know Teflon coated, which will be utilized for frying pan. So which will be Teflon coated. So that's where we have got the Teflon. So what is Teflon? Teflon is nothing but polytetrafluoroethene. Teflon is nothing but polytetrafluoroethene. fluoroethene. Right? So therefore, monomeric unit should be CF2 double bond CF2, N number. They will be used, and when it will get polymerized, it will become CF2 N number. That is nothing but Teflon. Fine. So now, in this case, once again, peroxide, radical mediated only. Even sometimes they will use persulfate for this particular reaction. They will be using persulfate. So what do you mean by persulfate? Persulfate is nothing but just like peroxide only, S2O8 minus 2. Persulfate means S2O8 minus 2. That means we have SO3O and another SO3. So that's where we have the persulfate. Fine. So which can go for once again cleavage, homolytic cleavage. So therefore they are called as persulfate. Per stands for two oxygen linked to each other. So persulfate, because we have sulfate SO4, we have sulfate SO4. But since they are linked through oxygen with single bond, therefore they are called as persulfate. Once again they will be free radical mediated. Fine. So another example for this one is addition polymer is PVC. So where CH2, CH, Cl. Fine. CH2, CH3. This will be the monomer or double bond. So double bond will be there. Now once again, under presence of radicals, they will get converted into CH2, CH2, CH. So that's where we have the PVC. Polyvinyl chloride. So where this PVC will be used, that is very commonly utilized for the water pipes, electric pipes, right? So that's where we have the PVC. Teflon in cooking utensils, like frying pan and all, they will be using Teflon, which will be resistant for the oils and grease. Teflon will be resistant for oils and grease. Therefore, it will be utilized for cooking utensils. But PVC will be utilized for something has it done. Amit. Yes, titanium tetrachloride and aluminium means triethyl aluminium zinc. Okay, so that's where we have the Ziegler-Natta. There is the presence of zinc, Amit. Fine. So that's what we were discussing about PVC. Where PVC will be utilized? It will be utilized for the water pipes and all, electric pipes. Everywhere PVC will be utilized because they will not conduct the electricity, one thing, and they are resistant for the waters also. So that's why they will be utilized in different water pipes and electric pipes. That's where we have the PVC. Anything I have left? Polyacrylamide. Okay, I have to talk about polyacrylamide. Fine. So we'll come to the next one, polyacrylamide. This one is also there, polyacrylamide. Now, when I am talking about polyacrylamide, so naturally monomer unit should be acrylamide. Okay. So now acrylamide is nothing but CH2, CH, Cl. So that is nothing but acrylamide. That is nothing but acrylamide. Fine. So now this acrylamide, I am talking about N numbers of acrylamide. Once again radical mediated, they will become just like PVC only, but instead of Cl it will be Cn. Nitrile group will be there. Okay. So therefore polyacrylonitrile also we can call. This one as polyacrylonitrile. Polyacrylamide will not happen because amide linkage is not there. I will make it as acrylonitrile and polyacrylonitrile. So that's where we have the polyacrylonitrile. Fine. So any other addition polymers? Okay. Done. So that's why it will be utilized for the fibers. Okay, na? This will be utilized as a fibers, polyacrylonitrile. I think these are the addition polymers. Okay, fibers. It will be used as a fibers. Like if I take, we have one material called as Orlon. It will be utilized in sweaters and even some of the beds, Orlon bed. So that's where polyacrylonitrile will be used. Even in combination with natural wool, it will be used. Yes, in combination with wool, it will be used. That's where Orlon material and all, they are made up of polyacrylonitrile. Fine? Any doubts? Okay, oil seals. Okay, fine. That is for Teflon. Already done. Fine. So that's where we have the polyacrylonitrile. I think these are the additional polymers. Important one I have discussed. So remember about their application. Application you should remember, and monomeric unit you should remember. Fine. So in that also Ziegler-Natta catalyst is important. That is nothing but tetraethyl aluminum and titanium tetrachloride, and sometimes even zinc can be included. But in your textbook, I don't know which one they have given. Okay, in your textbook, I think they have given not zinc, they have given triethyl aluminum with titanium tetrachloride, Ziegler-Natta. So you can remove the zinc then. We will go with the NCERT book only. So it will be triethyl aluminum and titanium tetrachloride, Ziegler-Natta catalyst. So what is that Ziegler-Natta catalyst? This is important. That's why I am telling this is many times. Ziegler-Natta catalyst is nothing but triethyl aluminum titanium tetrachloride. Okay, na? So that's where we have the Ziegler-Natta catalyst. I think Amit, he had written that one only that time. I didn't recognize. Amit, you were right. In your book they have given same thing. So triethyl aluminum and titanium tetrachloride. And Teflon, all these things, don't worry, they will not ask the structure and all, but they will ask application. They will ask the application. So you should remember about that one. And high density, low density polyethylene, that is important. Ziegler-Natta catalyst is important. Along with that, high density polyethylene and low density polyethylene is important. What is that difference between them? So low density polyethylene will be branched, but high density polyethylene is not a branched one. It is a linear polymers. And reaction condition you should remember. And what is Ziegler-Natta catalyst you should remember. So the application of Ziegler-Natta catalyst is it will provide the surface for the reactions to happen. So that's why a polymer will become highly dense. Fine. So these are some of the examples for addition polymers. Any doubt in this? Because tomorrow we are going to start with condensation polymers. But any doubt in addition polymers? So in that case, in addition polymers, what and all we have discussed? We have discussed about polythene. In that we have low density polythene and high density polythene. Then we have discussed about Teflon. What is Teflon? Teflon is nothing but polytetrafluoroethene. That is nothing but Teflon. Then we have discussed about polyacrylonitrile. Okay, polyacrylamide is condensation polymer. So polyacrylonitrile. So which is the monomeric unit? Monomeric unit is acrylonitrile. So another one. Any other things we have discussed in addition polymers? PVC. Another one is PVC, where polyvinyl chloride, where vinyl chloride is the monomeric unit. So they are all examples which we have discussed with respect to addition polymers. Fine. So you should remember this. And LDP, HDP is important. Along with that, Ziegler-Natta catalyst is important. So Ziegler-Natta catalyst, where it will be utilized? It will be utilized during the synthesis of high density polyethylene, not LDP, HDP. Fine. So in that case, remember, make the correction. I think I have told zinc also, right? So remove the zinc, keep only triethyl aluminum and titanium tetrachloride. Fine. So that's where we have the Ziegler-Natta catalyst. Remove the zinc. Once again I am telling. So what is the role of Ziegler-Natta catalyst? It will provide the surface for the polymerization. It will provide the surface for the polymerization. Don't ever write Ziegler-Natta catalyst with respect to LDP. If you are using Ziegler-Natta catalyst, then it will lead to HDP, no LDP. Fine? Okay, I will stop here. Any doubts? Okay, thank you. Take care. Fine?